So when we talk about electrolytes, big thing that we need to focus on here is dissociation / ionization, the breaking apart into ions. So in the picture here, you can see that we have a separation of that ionic substance into the mobile charged particles or mobile charged ions. So a lot of us struggled with this part here in previous units. So when we look at electrolytes, when we're looking at these, we're looking at the different ions. So when we talk about strong acids, when we're dealing with strong acids, we have our hydrochloric acid that's separated. You can see the free-floating ions. Based off from the free-floating ions, I know that strong acids completely ionize. Everything breaks into ions. More ions means that more electricity can be conducted, which means that this has a higher conductivity. When you look at a weak acid, such as that of ethanoic acid, weak acids only partially ionize. That means that you have less free-floating ions. Only a few ions means that only some electricity can be conducted. This is not a very good conductor of electricity, so your conductivity decreases. When dealing with electrolytes, remember, electrolytes means that you can conduct electricity when dissolved in an aqueous solution. This is something we've already dealt with. Contain mobile ions, charged particles. Okay, they are free-flowing or free-moving ions, like an ionic compound. So again, the structure dissociates. That those free ions allow the passing of electrons. That's why we call them electrolytes. Remember, metals are not considered electrolytes, even though they conduct electricity. They're a solid piece of metal, and they have free-floating electrons. They're not free-floating ions. That's why they differ. So when you're looking at the following, we want to classify each of the following and indicate if they're an electrolyte. So if they're an electrolyte, we know that they're ionic compounds. So we know that acids are electrolytes, we know bases are electrolytes, and we know that salts or ionic compounds are electrolytes. So H we know is going to break off, so we know this is an acid. So we know it's an electrolyte. KCl we know is a salt, which is also an electrolyte. CH3OH we know is an alcohol, which is not an electrolyte. NaOH we know is sodium hydroxide. Sodium hydroxide we know is a base, so we know that's an electrolyte. CH3COOH, the Cu group, we know that that's ethanoic acid, and we know that that's a weak acid. We're going to talk more about that in a little while. NH3 we know is ammonia, and we know that that is a base, so we know that's an electrolyte. LiCl we know is neither an acid or a base, but it is an ionic compound, so it is a salt. CH3CH2OH is just a longer alcohol, okay, that is ethanol, and that is one that 21 and older consume. For which of the following choices is the best electrolyte? So the highest concentration of ions. So here you're looking for the highest concentration, so we know that that's going to be 5.0 mole of HCl. Explain why a solution of 1 molar HCl, a strong acid, is a better electrolyte than a solution of a weak acid. Remember, what do strong acids do? They dissociate completely. Since they dissociate completely, you have more free-floating ions. Titrations. So this is something that we're going to actually do in lab. Titrations. What does it mean to neutralize something? So what is the neutral pH? You need to focus on the pH of 7, which means that you have the equal number of hydrogen ions as you do hydroxide ions. And what is molarity? Remember, molarity means that you have a certain number of moles per liter. So when you deal with titrations, in a titration, you always end up with a neutralization reaction. When you deal with a neutralization reaction, you always have the product of water and some type of salt. If you look at this, titrations, all they really are is a single or a double replacement reaction. You can see that the sodium switch place with the hydrogen, producing water and salt. In the second example, my acid and base, if it's going to neutralize, I have a double replacement, I have my production of water, and I have my production of my calcium bromide. Looking at the next one, I have my acid and my base. I have my double replacement, giving me my water, but also giving me my salt. Then in the last one, the same thing again, my water and my salt. All titration reactions and neutralization reactions produce a salt and water. So titrations, this is actually a process that we're going to be doing in class. Okay, chemists perform acid-base neutralizations, which are called titrations. Titration is an experiment that uses a burette in a mix of a solution to very accurately tell the amount of your hydrogen concentration ion and your hydroxide concentration. So we find out what the concentration is of the acid or the base. So in this, we're going to be using a burette. We're going to use our standard solution, which I'm going to prepare for you. Using the tap, you're going to dispense a solution, and you're going to actually see this by use of indicator change colors. And we're going to look for that color change, and that's how you can actually tell what the pH is based off of that color change. Standard solution is just an acid or base whose concentration is already known. You made it yourself. And what you're really looking for is the endpoint, which is signified by a color change. We're going to use phenolphthalein, or we might use bromothymol blue. Okay, change your indicator is a way to tell you have created a neutral solution. So your acids and bases. By creating a neutral solution, now what you can do is back check to see what your pH was to begin with. If you want a neutral endpoint using bromothymol blue, we would want to titrate until the color green. So you can see anything lower than 7 is yellow, anything higher than 7 is blue, and right smack dab in the middle is your green. You can use different indicators to identify different pHs. When you read a titration burette, it's the volume dispensed, not the volume in there. So if this was your reading, you are actually at 49 milliliters, not 1. Okay, so it's going to be, if you were to go all the way here, you would have dispensed 50 milliliters if you started at the top. You don't count backwards, you count down. Again, with this one, you would be at a little over 21 milliliters was dispensed. So you need to be careful on which way you're reading this. It's not up, it's down. Titrations, we're going to use a formula that's found on table T. Formula you should use to see, or to use for titrations is MAVA equals MBVB. Okay, since we're going to set these equivalent to one another, we have the molarity equals the volume equals the molarity and the volume. So the volume dispensed and the volume started with. When we're dealing with acids, we have different types of acids. We have monoprotic, diprotic, and triprotic. So monoprotic means that it contributes 1 H plus ion. Diprotic means it contributes 2 H plus ions. And triprotic means that it contributes 3 H plus ions. When you're dealing with these, okay, take into account how many ions each acid donates towards the OHs. So if you're looking at the following examples, HCl is monoprotic, produces 1 H plus. H2 is diprotic, so you have to multiply your Ma value by 2 because per mole there are actually 2 ions contributed. And then for triprotic, you multiply it by 3 because you actually have 3 ions contributed. So when you're using that titration formula, you have to use this multiplier based off of being mono, di, or triprotic. Same with bases. Bases can be mono, di, or tri. Mono produces 1. Di, you multiply your molarity by 2 because you're contributing 2 per dissociation. And then for tri, you have to multiply that by 3 because you're contributing 3 OHs. So when you're looking at practice problems with titrations, an unknown volume of NaOH is titrated in 32 milliliters at 0.1 molar of HCl. If the NaOH is 0.35 molar, what volume was required to neutralize? So you're going to use your MAVA equals MBVB. Plug in the variables you know. So I know the molarity of my acid, I know the volume dispensed to my acid, I know the molarity of my base, but I don't know the volume. So what do I have to solve for? VB. Since it's all monoprotic, I don't need any multipliers, and you just solve for VB, and you get 9.14. Second one, and both are monoprotic, so you're using MAVA equals MBVB, plugging in the variables you know. Solving for the one you do not. So what is the molarity of that acid? It has to be, the molarity of that acid would be 0.64 molar solution. Again, when you're looking at titrations, some things that the Regents exam finds more familiar. So what is the concentration of the NaOH? Look, are they both monoprotic? Yes, they are. So I know my initial reading, I know my final reading, so I know my volume displaced. So I take the difference. And I take my other difference, so now I know my molarities, I know my volume dispensed, and now I find the molarity of the base at 0.048. So diprotic and a monoprotic. So looking at your diprotic H2SO4, I have to use a multiplier. So I use MAVA, MBVB, I have to multiply my molarity by 2 since it's diprotic, and I solve for my variable that is unknown. Again, with this one, I have a diprotic base. So again, using the same formula, now I need to multiply this, so it's actually 2x. Solve for x, and you get 0.39 molar solution. Again, in another one, you're going to use the same setup over and over again. It'll get repetitive. So we talked about Arrhenius bases and Arrhenius acids. Arrhenius, remember, acids and bases. Arrhenius acid, remember, is an H plus donor. Bases are OH donors. So the shortcomings, or why we don't like that definition, is that limits acid and bases to aqueous solutions only. So you have to dissociate in order to be defined as an Arrhenius acid or base. Another problem is it doesn't explain why acids ionize. So why is that actually being dissociated and what's happening to it? Last part is it does not include bases without an OH ion, like our example of NH3. So a lot of people have asked me, why is NH3 considered a base? Here's why. We get into another theory. It's called Bronsted-Lowry. Bronsted-Lowry says that bases and acids are now based off from donating and accepting. So Bronsted-Lowry acid says that protons are donated. Okay, that makes you an acid. If you're a base acceptor, if you're a base, you are an H plus acceptor. Now you're going to accept that piece there. By accepting that, now you're considered a base. For example, if you're looking at H2CO3 in water, H3O is the acceptor, so the H2O was the acceptor, while this was the donor, so your H2CO3. We're going to use this because now by using conjugate acid-base pairs, similar compounds that differ by the presence of one proton or H plus ion, now we can identify who's the acid, who's the base, who's the conjugate acid, who's the conjugate base. So when you're looking at this, strong acids form weak conjugate bases. Weak acids form strong conjugate bases, and vice versa. So what does that mean? NH3 in my forward reaction I know is my base. So this has to be my acid. Based off from there, you have to see who changes into what. So H2O is the donor. That's why I know this is my acid. So if this is the donor on the forward reaction, in the reverse reaction, it's your conjugate base. So my NH3 is my base. In the reverse reaction, my NH4 must be my conjugate acid. It's donating, where my H2 in the forward is donating, but in the reverse is accepting. So H2SO4 and H2O. H2SO4 turns into HSO4, so donated, being the definition of my acid. H2O turned into H3O, so it accepted. There's my base. If my H2O on the left-hand side was the base, it's got to be the acid. And if H2SO4 was the acid on the left-hand side, it's got to be the base on the right-hand side. So again, these are linking, showing the flow of those protons, whether they're being donated or accepted. Amphoretic is just a substance that can act as either an acid or a base. Amphoretic substance that we're most common with is H2O. Substances that act both as an acid or a base, again, H2O can act as a base, it can accept, or it can be an acid and donate that H plus ion. Other compounds in amphoretic substances are some of the other ones found here, but the one the state focuses on the most is the water. So that's the whole unit. Acids-base chemistry takes a little bit of practice, but you guys can get used to it.